Hi friends, today we are going to study the solid state physics. In this class, I am going to discuss about crystals and something about the symmetry of these materials. And solid state physics mainly deals the crystals and electrons in crystals. Solids are mainly classified into three types. They are crystalline, amorphous and polycrystalline. In this we know crystals, why crystals are important. First thing, nature loves order. In crystal we can see a order, regular periodic arrangements of atoms or molecules we can see in crystalline materials. In nature, many materials we can come across. In this, in our nature, you can see silicates and biological materials, inorganic materials. In this inorganic components or inorganic materials, we can see mainly in the ground, they are in the form of silicates. Silicon and oxygen components are mainly there. But why crystalline material important? Crystals we can see long range order of atoms or molecules. In amorphous materials, there is order limited to few molecular distance. But in polycrystalline materials, they are made up of grains which are highly ordered crystalline regions of irregular size and orientation, but of course, there is also short range order of atoms or molecules. That is why they are called polycrystalline materials. There are so many grain boundaries you can see in these particular kind of materials. So, in short, we can say crystal is a solid where the atoms or the molecules form periodic arrangements. The crystal form develops as identical building blocks are added continuously. The atomic arrangement in a crystal is called crystal structure. We can see crystals not only in our nature, but also in our body also. We can say cholesterol. Cholesterol is a type of crystal which are composed of carbon, hydrogen, oxygen, and these some inorganic component also introduced in this material. It becomes grown in the form of polycrystalline material. Now, if we want to discuss about the properties of crystal, because you know that crystals are regular periodic arrangements of atoms or molecules, then there may be, if an atom is there, around atom a cloud of electrons are there. These electrons are oriented or in a particular way, and the property of the materials mainly depends upon how these electrons are behaves. So, if a molecule is there, atoms are there in molecules and a cloud of electrons over or in the purview of molecules behave in a particular kind and its physical property like electrical property, magnetic property and even mechanical properties also depends upon this. So, we know that some materials or some crystals are very hard in nature and some are very soft. All these are depends upon how atoms or molecules are arranged in it. I already told you a crystal is a periodic arrangements of structural units which are in 3-dimensional. So, 3-dimensional periodic arrangements of atoms can be considered as a perfect crystal. But here when we look into in detail how atoms turns to crystal and how periodicity is continuous throughout the crystal. So, first when we discuss into crystal, lattice points is one component. The points in space about which the atoms are located, that is lattice points. So, mathematically we can say lattice points are regular periodic arrangements of points in space. In this particular point, we can see in these points there may be atom attached to it, or sometimes molecules attached to it, or a group of atoms or group of molecules attached to these each lattice points. So, then lattice and these atoms attached to these points together makes the crystal structure. So, space lattice or crystal lattice. An array of lattice points in space such that every point has identical surroundings. The atoms or the molecules associated with the lattice points are called motif or basis, and together atom plus or lattice plus basis called crystal structure. When atom or identical group of atoms is attached to every lattice point, we obtain a crystal structure. Here I already told you these lattice points are there, and attached to lattice point atom may be there. In the same point there may be attached atom, or around these you can see a group of atoms attached to this particular lattice point. Example, if this is chlorine atom and this is sodium. So, a sodium chloride molecule or sodium ion and chlorine ion attached to this particular lattice point, we can see that this in this way the sodium chloride crystal is growing, or which are growing in 3-dimensional way, we call it is a 3-dimensional crystal. So, we can have 1-dimensional, 2-dimensional, 3-dimensional arrangements of atoms. For simplicity, everyone discuss 1-dimensional case initially. In a given direction, all lattice point must be separated by an identical distance a, which we called lattice parameter. Here, look at here, you can see these lattice points, 2 points are separated by a distance. If you consider only one dimension, that is x alone, then these particular distance, the distance between 2 nearest points, this called lattice constant, this commonly we say lattice constant or lattice distance. The order or the unit of this particular distance is length, the unit of length, commonly we discuss it is nanometer or angstrom. In 1-dimensional lattice, a translation of this A, this translation of this A, here we can see this 1, 2, 3, then simply we can call this 1, 2, 3 as n, an integer. So, the distance we can call this total distance may be n into A. In many cases, we have to calculate this and how the phonons are propagated in crystals, or how the lattice vibrations are propagating in crystal, etc., where we need these type of calculation. For theoretical representation or theoretical explanation of property of materials, these parameters are very much important. In one dimensional lattice, a translation of n A from one lattice point to another, where n is an integer, brings you an identical lattice point. Starting a point, lattice translation vector or basis vector can generate a lattice. So, translation vector is very important when we calculate how the atoms are arranged and how the crystal is growing and in which direction this particular growth vector is moving, etc., are very important when we discuss about 3-dimensional arrangements of atoms or molecules. So, one dimensional lattice first initially we are discussing, and where translation vector we can simply write T is equal to n A. N is integer. Next one is 2-dimensional lattice. In 2-dimensional lattice, the same thing, because in 1-dimensional lattice the atoms are separated by a distance in x axis, or we take A. Similarly, in 2-dimensional case, here you can see the points are in space. This we take A, and this we can take, this particular case we can take as B, A and B. There are two non-collinear basis vectors A and B. A translation of n A plus P B, here n is integer and similarly P also integer, and P along y axis and n along x axis from one lattice point to another brings you to an equivalent lattice point. And when we two vectors are there, there corresponds an angle between them. This angle is also very important when we discuss the crystal structure, and this interaxial angle gamma defines the relationship between two vectors. These angles are also very important, and here when translation vector T is equal to n A plus P B. This here n and P are integers 1, 2, 3, etc., and interaxial angle is here in this case you can see this is 90 degree. In this particular case, that also varies in different types of crystals structures. And when we discuss real crystal, we discuss 3-dimensional lattice. In 1-dimensional lattice and 2-dimensional lattice are very important when we discuss 1-dimensional material cases and 2-dimensional material case, etc. It is very important, but 3-dimensional case, real case, or when a crystal is growing in nature, it is 3-dimensional case. Here we are going to discuss 3-dimensional lattice. What is 3-dimensional lattice? There similar in the case of A, B, there may be another axis also, that you can see A along x axis, B along y axis, and C or C along z axis. Then this translation vector correspond to 3-dimensional material. It is n A plus P B plus Q C. So, translation vector, when how the atoms are growing, we can see that n A plus P B and Q C, and this n number, P number and Q number are higher and higher when a crystal is growing bigger and bigger. So, this particular integer and translation vector is very important when we discuss different properties of crystals and different planes how growing in crystal. When we consider the morphology of the crystal, there also these particular parameters are important. We know that the morphology, when we are seeing a crystal, you can see the surface may be plane or surface may be in a particular way you can see. So, these geometry of the crystal are very much important, and these particular translation vector in which direction it is growing. So, this translation vector n, the integer in the case of translation vector you can see T is equal to N A plus P B plus Q C, and the value of N, P and Q are important, which makes the shape of the crystal while you are seeing after growing crystal in a bigger size. So, if the direction of growth is and the growth rate is small, in which direction the growth rate is small, you can very easily see that particular direction have a particular shape. The lowest growing direction gives the shape of the crystal. If larger means the length, sometimes it is breadth, but a fine phases we can see in which direction the crystal is growing in a relatively smaller way, smaller growth rate. Another important parameter or important thing we have to discuss is unit cells, because I already discussed you 3-dimensional arrangements of atoms or molecules, and this 3-dimensional there may be a unit, particular unit is there, and this unit is regularly repeating in bulk crystals. So, in a crystal there may be a fundamental unit. This fundamental unit is just like while you are making a house, the fundamental unit is brick. Similarly, these bricks are arranging in a particular manner, we make very beautiful houses and similarly very beautiful structures by keeping these units in a particular way. Similarly, in crystals there is also unit cell. That unit cell is made up of atoms or molecules, and these units are regularly or repeating 3-dimensionally to form bigger crystal. So, in every crystal some fundamental grouping of atoms or molecules is repeated. Such fundamental grouping is called a unit cell. So, fundamental grouping of atoms or molecules in a 3-dimensional way, that is called a unit cell. Unit cell is a basic structural unit or building block of the crystal structure. The smallest repeating unit formed by combining basis vector, combining the basis vectors are unit cell, and unit cell retains all the characteristics of the lattice. A unit cell is a unit or the structure that is a line segment in 1-dimensional, a parallelogram like shape in 2-dimensional, and parallelepiped, a parallelepiped in 3-dimension, such that lattice points are at the ends of the line segment 1-dimensional or at the vertices of the case of parallelogram, that is 2-dimensional. In the case of parallelepiped, that is 3-dimensional, which when repeated by the translation symmetry vectors generates the whole structure. So, we can see in the 2-dimensional case there may be a angle between two axes, and in 3-dimensional cases you can see a corner, and atoms may or molecules may be attached in that corner also. So, unit cell, when we say this particular unit cell, these unit cell are repeating in the in a crystal in a 3-dimensional way. So, first atoms, and then atoms in the case of sodium in the case of aluminum crystal, their aluminum atoms are the simple unit. In the case of sodium chloride crystal, you can see sodium and chlorine, that is molecule, and this molecule made unit cell. So, in a here in this 3-dimensional structure, so you can see here these are lattice points, 3-dimensional lattice points. Attached to these there may be a molecule. Here also attached to this there may be a molecule. In this corner also there may be a molecule. So, in that way the sodium chloride crystal unit cell is there. So, we can see here in this sodium chloride crystal, everybody knows sodium chloride, structure of sodium chloride is FCC, face centered cubic. I will discuss in that case detail, but here example you can see a simple cubic structure or a cubic structure. We can see all the corners are containing a group of atoms attached to this particular point, that is called lattice plus basis. In that way this particular crystal structure forms. If it is sodium chloride, of course, in the face center also there may be a group of atoms attached. So, we can see this is a 3-dimensional case, 3-dimensional cell. So, here when we discuss this particular unit cell, there may be different kinds of unit cells are there. So, if only corners are having atoms or molecules, and similarly some body center of this particular cube may contain one atom or group of atom. Unit cell can be completely described by the 3 vectors A, B, C and the angles between them alpha, beta and gamma. Here you can see the B angle between B and C alpha and C and A beta and B and A, that is gamma. Lattice parameters: axial lengths A, B, C, interaxial angles alpha, beta, gamma, and unit vectors in the along x axis A, along y axis B, along z axis we call C. Or here in this case you can see all those things in this particular picture, and all unit cell may be described via these vectors and angles. So, these unit cells are the building block of any crystal. Next is primitive cell. Another type of unit block is primitive cell. It is sometimes primitive cell may be unit cell, but all unit cells are not primitive cell. That is very important. Here in primitive cell, it is a geometrical shape which when repeated indefinitely in 3 dimensions will fill all space and is equivalent of one lattice point. So, we can see in 3-dimensional crystals these identical building blocks are repeating there also, but in primitive cell is a unit cell that contain one lattice point only at the corners. So, that is very important. In primitive cells, lattice point only at the corners, but in unit cell it may not be. So, if there are lattice points in the cell other than the corners, the cell is non-primitive. So, in the case of a unit cell may be non-primitive also, but in primitive cell the atoms attached only in the lattice point attached in the corners only, but there may be atoms or group of atoms may be attached other than the corners in the case of unit cells. we previously discussed unit cell. This also we consider in one dimensional way, in two dimensional way and in the three dimensional way. But unit cell of a one dimensional lattice is a line segment. We already say, how can you say a unit cell in one dimension? Because unit cell we already discussed, that is in a three dimensional repetition unit. But when we look into the theory behind the crystal growth and theory behind how electrons are propagating or electron clouds around an atom, there we need a one dimensional explanation for how a primitive and unit cells behave when atoms or molecules are arranged in x axis or y axis or z axis alone. But we already know that particular one dimensional growth is very difficult to obtain in a material, but one dimensional growth we can see only in nanowires, where nanowires also, even though we are saying one dimensional, the other direction in x and y direction and z direction there are atoms or molecules, but compared to the x axis the parameters, because the length parameters are relatively small, we can say that the atoms, the confinement is there of atoms or molecules are confined in that two direction, then the length parameter or length along the x axis only we are considering matter. So, unit cell of a one dimensional lattice is, that is why important. So, why everybody is saying if two dimensional means that is a space, and three dimensional then only bulk crystal forms, but one dimensional unit cell of a one dimensional lattice is a line segment of length equal to the lattice parameter. This is the primitive unit cell, that is it has one lattice point per cell. In primitive unit cell, each of these lattice points contributes half a lattice point to the unit cell. Doubly primitive unit cell contribute to the unit cell left point, that is equal to 0.5, and if we consider middle point, that is equal to 1, and one point right to that is again that is equal to 0.5, half of the contribution. So, we contributes in this particular lattice, you can see the atoms are attached to lattice points, that is here contribution and these distances are there, and this distance is a, and if these three are together, we can see that this part contribution, this also there. So, three lattice points we consider together, then unit cell is non-primitive, but if two only we take, it is primitive case. Unit cell non-primitive, and similarly if more than this, here three lattice points, if this is also we consider into add into this. So, these 4 lattice points together. In the case of 4 lattice points together, there we call triply non-primitive unit cell, triply non-primitive unit cell, that also not primitive. Primitive means corners having one lattice points. If one lattice point here, and in two dimensional case you can see similarly here also this, and these are there in this direction also. Similarly, in three dimension also there, but triply non-primitive unit cell, doubly non-primitive unit cell and primitive unit cells are clear from this particular picture. And in case of two dimensional case, in two dimension, similarly if lattices are there, space lattice, 2 dimension, you can either take like this or here it does not means here only you can nearest lattice point only you can attach, but you can attach another shape like this or another shape like this and like this. So, here shape you can see this is square like and here just like a parallelogram like, and this also in this way also the unit may be repeats, there also forms crystals. Here this way nearest lattice points are only attached and in this way the crystal may be grows in 3 dimensionally in space. So, that also turns to a crystal. So, here we can see these two are rectangular lattice, this is rectangular and this also rectangular. The only thing this is a square, this is a parallelogram and the angle between this is 90 degree and this may be different, this is not equal to 90 degree and this may be more than 90 degree, but here all are 90 degree, that is the main difference. In this 2 dimensional case also primitive cells, all the corners are having lattice points and doubly non-primitive cells and also triply non-primitive cells. These all primitive cells we can construct in a rectangular lattice. Notice that symmetry of the lattice of the crystal is not altered by our choice of unit cell, it will not affect. 4 unit cell shapes in 2 dimension case, they are oblique lattice, square lattice, rectangular lattice, hexagonal lattice. In oblique lattice, A not equal to B and gamma the angle between them are arbitrary, and in square lattice A equal to B and the angle between A and B, that is gamma is 90 degree. In rectangular lattice we can see A not equal to B and gamma equal to 90 degree. In hexagonal case this A equal to B and the angle between them, that is gamma, that is equal to 120 degree. So, they are the 4 unit cell shapes in 2 dimensional case. But in 3 dimensional crystal you can see that there are 14 distinct 3D lattices which come under 7 crystal systems. So, 3 dimensional crystal systems are as showing here, edges and angles are in the first picture and cubic case A equal to B equal to C, that is, and the angle between the vectors or in angle between the directions alpha is equal to beta is equal to gamma, they are 90, and tetragonal systems A equal to B not equal to C and alpha equal to beta is equal to gamma, they are 90 degree. In orthorhombic crystal systems, A not equal to B not equal to C and the angle between them alpha equal to beta equal to gamma, they are 90 degree, and another system monoclinic A equal to B, A not equal to B not equal to C and alpha equal to gamma is equal to 90 degree and not equal to beta, and here beta is not equal to 90 degree. And in hexagonal system we can see A equal to B not equal to C and alpha equal to beta equal to 90 degree and gamma is equal to 120 degree. 120 degree. In the case of rhombohedral systems, the A equal to B equal to C and the angle between them, that is alpha equal to beta equal to gamma not equal to, here alpha equal to beta and gamma not equal to 90 degree. So, here alpha and beta and gamma they are not at all equal to 90 degree. And triclinic system, A not equal to B not equal to C and angles alpha not equal to beta not equal to gamma and they are not equal to 90 degree. So, these are the 7 crystal systems, and correspondingly in these 7 crystal systems there are 14 distinct 3-dimensional lattice also we can see. In this class we have discussed crystals, crystal structures, primitive cells, unit cells and 7 crystal systems. Thank you for watching this session. See you next time. Bye.